Welcome and hello. This is a video lesson in the FHWA hydraulic toolbox. In this lesson, I'm going to be discussing channel lining design calculator. So if you go up to your FHWA hydraulic toolbox and you want to click on calculators, the second option here is new channel lining design analysis. We'll create an analysis, i.e. a calculator for our channel lining design. In the FHWA hydraulic toolbox, the channel lining design calculator is a tool for determining what type of thickness and channel lining is needed to prevent erosion or failure of an open channel given certain flow conditions. Right here is the user's manual for the hydraulic toolbox. I'm on page 20, the beginning of chapter 6, where it discusses the channel lining design calculator. This is the interface we'll be talking about in this video and going through a few different examples. Also, I have a couple other PDF files that you're going to want to download if you want to follow along in this lesson. They are linked in the description of this video. They are the HEC number 15, Design of Roadway Channels with Flexible Linings. And then the second one is the FLH FP14 Standard Specification for the Construction of Roads and Bridges on Federal Highway Projects. Both of those documents are PDF files. So go ahead and download those and let's go ahead and get started. So back to the user's manual. This is the little icon right here associated with this calculator, the channel lining design calculator. It's just like a roadway beside a waterway right here. All right. So as we scroll down, what we learn is that there are 4 options for channel lining in the design calculator. They are rock, which is small riprap, cobble, and gravel, vegetation, rolled erosion, and then on the next page, Gabion. Further down this page, page 21, we have a flow chart. And basically, this is the methodology to determine whether or not the lining for erosion protection is acceptable or not. So if you scroll down towards the bottom, then we have this final question. Is the permissible shear stress greater than the expected or calculated shear stress times this SF safety factor? If it is, then the lining is acceptable. And if not, then you go back to a previous step, select the lining, and perform some other equations and calculations with specific data input based on your design. Okay, so let's go ahead and run through the examples. As soon as you open up that calculator or the analysis tool right here, I'll go ahead and just rename this real quick to Channel Lining Design 3, or how about just Channel Lining 3, like that. Okay, so there's the icon. I'll go right click and Channel Lining Design Data, or you can also open up this dialog box by just doing a double click. All right, so the first question we need to ask ourselves is what is the lining material? And that is the first drop down at the very top here. Our options are the 4 that I already read from the user's manual: riprap, cobble, or gravel; vegetation, like grass, for instance; rolled erosion, controlled product; and rock gabions, the mattress style. So let's just go ahead and do these one at a time. Riprap, cobble, or gravel. The first thing we need to do is provide channel parameters. That's flow data, cross-section data, Manning's N, and so on. After that, we need to provide input parameters that are specific to our lining. After that, we'll get some results. We can also add a optional bend shear curvature of radius if we wanted to check for bend shear. But basically what we're first going to be checking for is bottom shear and side shear, and then bend shear only if we add a specific curvature of radius. Okay, as for this channel parameter data, this is something we only need to provide once. And then as for the input parameter data, we'll have to provide that for each of the 4 different lining methods that we select up here. So let's go ahead and knock out the channel parameters first. What we can do is select an existing channel like channel 1 or channel 2. Those are the channels that I already have defined in my project, channel 1 and channel 2. Or I can create a brand new channel, which would just say create new. And then I'd click on channel calculator. All right, so this should be familiar if you've used the channel calculator tool before. It's basically the same thing. Let's go ahead and do that. So I'm going to say that the shape is trapezoidal. That's done. The side slope, I'll say, is 1:1. And then this is in English units, so that's good. If it's not English units, you can switch it to English units if you want to follow along and use my numbers. Otherwise, you're welcome to use metric, doesn't matter. The bottom width I'll say is 5 feet. That's B. Longitudinal slope I'll say is 1% slope. And then Manning's roughness I'll say is 0.035. And then the flow, the design flow rate I'll say is 10 CFS. And then I'll click calculate. Here are the results. So now I just click on OK, and then boom, here are the numbers that were calculated that will be used for determining whether or not the lining data that I provide is satisfactory to prevent erosion. All right, so first up is riprap, cobble, and gravel. So the parameters here for input parameters is specific to this lining method. If I switch to vegetation, we're going to have different input parameters. If I select to ruled erosion control product, different input parameters. So that's how that works. D50, this refers to the diameter of the median design size of the rock by mass. So it's just, I'm just making something up here, say 25 millimeters. Riprap specific weight, I'll go with 165. Typical range is between 150 and 170. That's in pounds per cubic feet. And then specific weight of water, 62.4. That works. If it happens to be salt water, you'll probably use something closer to 64.4. The riprap shape or options here are crushed, angular, or rounded. I'm pretty sure that either crushed or angular will provide the most erosion protection. Rounded, probably not so much. Oops, hold on a second. So the side slope of the channel is greater than the angle of repose. 1 second. Okay, one change I'm going to make is to change this side slope from 1 to 1 down to 4 to 1. So let me open up the calculator, then change this 1 to a 4 and this 1 to a 4, and then that shouldn't be a problem anymore. Okay. All right, the last data we need to input is the safety factor, 1. In fact, I should probably bring up the user's manual and go down to this section for rock lining. This is what we're dealing with right here. This tau sub P value is the permissible shear stress, which equals this F sub S value, which is the shields parameter, which we have in this table down below here. And then the safety factor. Then we have our unit weights, and then the D50 value. So this permissible shear value right here, if we scroll up to our final check, is what we're calculating. It needs to be, the larger the permissible shear, the more likely that the lining design will be satisfactory. Here is the SF, that's the safety factor, and then this tau sub D, that's the calculated amount of shear based on the hydraulics of the channel data that we already put in. The user's manual does a pretty good job at referencing the HEC 15 document, equation 6.7. So let's go ahead and check that out. Okay, here it is. Permissible shear stress, it's the same equation, except this time the variables themselves are detailed out. Looks like the D50 is now in meters. So I'm just going to trust that the software is working and can make that conversion. All right, so after all that's been done, I'm going to scroll down, and here we have our results. In green, it looks like for passing, the message here is that the channel bottom is stable when it's checking for bottom shear. And then the next green message down tells us that the channel side is stable when checking for side shear. So when all of the parts are stable, then the final stability check says that the channel is stable. If the channel is not stable, then basically we would just change some of our input parameter data. So for instance, if the D50 is smaller, let's go ahead and change that down to 10 millimeters, and I'll tab off and then scroll down. Looks like we are not stable at the channel bottom or at the channel side. So let me go ahead and put that back to 25. Let's say the safety factor needs to be larger. Instead of 1, maybe it's 1.5. Let me tab off and then scroll down. Okay, again, we're unstable. Let's increase the mean grain size to 50 millimeters now, and then tab off. And now we're stable again at that higher safety factor. So sometimes you need to play around with the input parameters for your riprap, cobble, or gravel lining method to make sure that your channel is stable based on the flow data. Okay, so moving on, let's go to vegetation. Vegetation refers to grass. We've already inputted the channel parameter data. That's the design flow of 10 CFS, the trapezoidal cross-section with a 5-foot base width and a 4 to 1 horizontal to vertical side slopes. So we don't need to do this part anymore. But now with vegetation, we do need to input distinct input parameter data. Specific weight of water, we'll leave that at 62.4. Height of the vegetation, this is referring to the height of the grass. So 0.333 feet would be 4 inches. Maybe the grass is shorter, but the longer the grass, the more erosion protection that it provides. Condition of the vegetation, our options here are excellent, very good, good, fair, or poor. So excellent would be a very healthy grass, a very dense grass. Poor would be a very sparse grass, a very weak grass, or unhealthy grass. This is essentially a qualitative assessment of how much erosion protection the vegetation can provide under flowing water. It's associated with the density and coverage, root strength and depth, and then maturity of the vegetation. Growth form of vegetation, our options there are sod, bunch, and mixed. And then the C sub F variable here, 0.75. Let me go ahead and bring up the calculation for permissible shear stress for vegetation first. So back to the user's manual, I'm going to scroll down to 6.2. I'm on page 23 now. Here it is. Tau sub P is our permissible shear stress. This C sub F variable is the one that we're talking about now. This is the grass cover factor. See page 59 in the HEC 15. So that is right here, HEC 15, page 59. Okay, here is the same equation we were just looking at. C sub F is the grass cover factor. If I scroll down a little further, this table 4.5 tells me what the cover factor is. So it's going to be as low as, say, 0.41 for poor and bunched, but as high as 0.98 for excellent and sod. So this plays a big difference in the calculation for permissible shear stress. Let's head back over to the calculator now. What it's telling me is to see that exact table. Default is 0.75 for a good cover factor and mixed growth. Let's just go ahead and leave it there for now, but this is something we could come back to later. All right, soil type, non-cohesive. Our options are either that or cohesive, so maybe a sandy soil. And then D75, 2.54 millimeters. Let's just leave it at that. And then a safety factor, once again, of 1.0. Now with all these values provided, we should be able to scroll down and check the bottom is stable, and that makes the channel stable. If we wanted to play around with the channel bottom stability, we can mess around with some of our input parameter data. So if I said the safety factor was ridiculously high, like 3.5, and then tabbed off, the bottom would not be stable. But if I then increase the height of the vegetation to something like, how about half a foot, okay, and then tab off, then the channel bottom is stable because the extra height of the vegetation now provides extra protection from erosion. Let's go ahead and change that back to 0.333, so 6 inches down to 4 inches again. It's unstable. But now let's change that C sub F value, the grass cover factor, from 0.75 up to 0.9. And then if I tab off, boom, it looks like we're stable once again. The curvature of radius, let me go ahead and add a curvature of radius. How about something fairly large, like 1,000 feet? Okay. Wow, still not stable. That's probably because our safety factor is still 3.5. Let's lower that down to 1. So effectively no safety factor. Okay, so it looks like we're still unstable. Not rely on vegetation for a bend. Let me just change that back down to 0 and then tab off. And okay, so it looks like it's stable again. It's not even running the bend shear test. All right, the next lining method is rolled erosion control product. If you read this in the literature, it sometimes is abbreviated RECP. So I might say that, RECP. We have our channel parameter values. Now the input parameters are right here. And now it's referring to a different document. This is the FLH FP14, which is what it's asking us to provide a shear stress of the RECP in pounds per square feet. So let's go back to the user's manual first, then scroll down to RECP lining. Here's the equation in the HEC 15, equation 5.5. Chapter 5 begins on page 75. But if I scroll down to 78, here is the equation for permissible RECP, soil shear stress. Boom, right here. Tau sub P is the permissible shear stress. But what we need for that first parameter is over here in the FP14 PDF file. I'm on page 826, or it says 846 of 902, whatever. 713.17 rolled erosion control products, and then it lists a number of the different products here. They're labeled out type 1A, ultra short term netting or open weave textiles. This is pretty much the cheapest quality, the least protection. And then as you increase in number and letter, type 1B, type 1C, type 2A, type 2B, all the way to type 4B, we have long-term erosion control blankets. So each of these different types here, if you scroll down, is a column in this table 713-3. And the parameter that we're looking for is this fourth row down here, minimum shear stress. So the values range from 1.00 up to 2.25. And then this footnote 5, kind of hard to read because it's small, but that's referring to the half-inch erosion threshold that's mentioned in the calculator. So anyway, the takeaway is the values are going to probably range between 1 and 2.25. Let's go back to the calculator and just use the value of 1 for now. Input Manning's values as user-supplied end value. So you can either go user-supplied or manufactured. If you go manufactured, you'd have to type in your own Manning end value. So I'm just going to go with users supplied, and that's going to be based on the RECP type, either open weave textile or erosion control blankets or mats. We saw these descriptions in that FEP 14 document right here. So we have open weave textiles, and then the next one down is a blanket type. So let's just stick with open weave textile. Manning's N, we'll just use 0.025. Looks like here's the range, 0.022 to 0.028. Specific weight of water, we'll keep it at 62.4 pounds per cubic foot. The soil type we'll say is non-cohesive. D75, I'm just going to use their example number of 2.54 and the safety factor of 1.0. If we scroll down, we should see our results in green. That means success. The maximum shear stress on the channel bottom is 0.296 pounds per square feet. And then the permissible shear stress on the RECP is 0.518. So plenty of extra erosion protection there. If we increase the shear stress value from that table, say we used 1.5 instead, tabbed off, and then, that only increased the permissible shear stress of the RECP, now up to 0.777 pounds per square foot. So even more protection. If we change the soil type from non-cohesive to cohesive, now we need to provide the plasticity index and the void ratio. So let's go ahead and do that. I'll just use some typical numbers here. So for plasticity index, we'll just say it's sort of a medium clay. And then for void ratio, I'll also say it's about medium, say 0.8. So I'll tab off, scroll down. It looks like the channel bottom is still stable. Okay, let me go ahead and make it a little bit less stable by changing the properties of the clay. I'm going to say the plasticity index is less, maybe 10 or 15. And then, so that'll be a weaker particle bonding. And then for the void ratio, I'll increase that. I'll increase that from 0.8 up to 1.5. So that is a looser clay structure. And then I'll tab off. Wow, looks like we're still good. Let's change this back down to 1. Okay, it looks like my hydraulics just make it hard for this particular channel bottom to go unstable. All right, and the last lining method I'm going to discuss in this lesson is Gabions. Again, we have the channel parameters set. That's good to go. Here are our input parameters. And before we get to that, let's look up the equation. So back to the user's manual. Now I'm on to Gabion lining. This is the fourth 6.4 channel lining design calculator for Gabions. Here is the equation for permissible shear stress. It's equation 7.2 in the HEC 15 document. And I found it. It's right here, where MT and MT sub C represent the Gabion mattress thickness and the thickness constant. Okay, nice to have that description. The D50 value I'm going to say is 30 millimeters. And then the Gabion specific weight, 165. That's cool. Gabion mattress thickness in feet, I'll say it's 3 feet, just making up numbers. And then the safety factor of 1 results in a permissible shear stress on the mat thickness of 5.2 pounds per square feet, which is much more than the 0.382 pounds per square feet, which is the maximum shear stress on the bottom. So we definitely have stability when using the rock gabions. Let's check out that radius of curvature now. So instead of 0, let's say 1,000 feet is our radius. Okay, so it looks like we're passing the bend shear test. Let's go ahead and change that to something less. How about just 100 feet, which is a rather small radius? And okay, looks like it passed again. The bottom of the bend is stable, so the channel is stable. There's also at the bottom some recommendations as far as the distances, minimum distance to extend upstream of the region, and then also downstream of the region. That's the sort of the region of interest, the area that's most likely going to erode, as well as a few other parameters, recommendations. So that is it for this lesson. We used a few different PDF documents to guide us through learning about this calculator. It is the channel lining design calculator that helps us understand what is needed to prevent erosion or failure from an open channel under given flow conditions.